Hey, thanks. I'm really happy to be here and to have the opportunity to give this talk to all of you. So luckily also we had some nice motivation for this kind of story earlier this morning. And the idea is that, it's very possible that the dark matter could be more similar to than dissimilar from the baryonic matter. And further, if we're a bit unlucky, it could be the case that the only coupling that this complicated dark matter has to the baryons is through gravity. So in some sense, this is, a grim possibility, sometimes referred to as the nightmare scenario. But even in this case, we can get some really interesting insights from gravity alone. And in particular, I'm going to be talking about the insights we can get from the mergers of compact objects that are going to be visible in gravitational waves. And I want to emphasize that this is something that, usually when we talk about dark matter, we're thinking about scales sort of from galaxies out to Hubble volume. And here we can see down to scales of like kilometers, which is really exciting. And the mass spectrum of these merging compact objects can actually tell us about the physics of the dark matter, the fundamental physics. So I'll actually mention also, though, that, the ingredient that we need to realize this dark compact objects is some dissipation mechanism, right? So we need some light particles that the dark matter can spray off and get rid of kinetic energy so that it can get down to, very high densities. And this is not just an abstract proposal, right? This is something that can be observed. LIGO has some sensitivity that in fact goes down to a space where we expect there to be no astrophysical binary mergers. So anything in this subsolar mass range where we can see even in 2018 out to, tens of megaparsecs is a dark matter discovery. So with this in mind, I want to talk in sort of general terms about how we can think about forward modeling from the dark particle physics towards the spectrum of dark compact objects that we could end up with. And there are various levels of sophistication that you can do this kind of estimate at. And I want to just go through a few of these. So first, there's going to be something like a Chandrasekhar limit, and that's going to be pretty much immediate once you write down your theory. Then you can think about, eventually the dark gas is going to become optically thick and your cooling mechanism will become ineffective, and this will put some limit on the collapse process. So that's the opacity limit mass, and this people are working out in various models. And this is like kind of a lower bound on the mass of compact objects you could end up with. And then I think kind of an upper bound is like, what's the scale of the gravitationally unstable cloud? So where does this collapse process begin? And this is a bit more complicated, and I'll talk about that in the talk. And then finally, if we want to know something like the dark initial mass function, that's going to be really hard, right? And even for the case of baryons, we really, there's still debate about the universality of the initial mass function and the origin of its shape. So we're not there yet. So I want to introduce some of the tools that are going to be useful. And for me, the most fundamental of these is the relationship between density and temperature that comes about over the course of this collapse. So here, this is for the collapse of a baryonic gas cloud cooled only by molecular hydrogen. And as the density increases, we see these features in this temperature curve that are basically set by the thermal physics, the microphysics of the gas. So initially, cooling is ineffective. We heat up. Eventually, we form some hydrogen molecules and cool down. The cooling saturates. Gravitational instability sets in. We have, a bunch more complicated and interesting effects. And eventually, we form a hydrostatic core that's surrounded by this gravitationally unstable envelope that's going to accrete onto it. So of course, the correct way to generate this kind of relationship between density and temperature is to do three-dimensional hydrodynamic simulations. But it turns out that a lot of the time you don't need to do that. That's a stronger tool than you need. Because as I mentioned, this is really controlled by the microphysics, not by the dynamics. And so you can do what's called a one-zone calculation, where you say now the density is just a single number that you can think of as you want, if you want, as like the density in the center of this cloud. That's evolving on some characteristic timescale, say the free fall timescale. And then you can just evolve the density and solve for the temperature and, if appropriate, the chemical abundances. And you can get back this shape that we see, you know, when we do the full analysis. And okay, so usually this kind of one zone calculation involves solving a system of ordinary differential equations. But actually the physical intuition is even simpler. And the idea is that as we evolve towards higher density, we're following this trajectory where the cooling time scale is the same as the collapse time scale. So what that means is that if, you know, I'm at some point where my temperature is really low, I'm going to heat up until the cooling becomes effective again, and then I'll follow this. And if I'm at some very high temperature, then my cooling rate will be really big, and so I'll cool down towards this trajectory again. So that means that I don't even have to do the full one zone calculation. I can just do this time scale, equate the collapse time scale to the cooling time scale, and get back this same relationship between density and temperature. And here I've drawn in some lines of constant Jeans mass, which we'll come back to. So these were some sort of general ideas that I introduced in the context of the collapse of a baryonic molecular hydrogen-cooled gas. So now I'm going to talk briefly about dark matter, which is what we're here for. Going to be talking about the mass scale I mentioned, the opacity limit for atomic dark matter. So in atomic dark matter, this is sort of from my perspective, a way that we can realize these interesting dissipative physics in a tractable but realistically complex environment. So we have a heavy fermion that's like a dark proton. We have a light fermion that's like a dark electron, and these are coupled by a massless photon. And the final parameter that I'll mention is this temperature ratio between the dark photon temperature and the CMB temperature. And as promised, the Chandrasekhar limit comes out immediately from just these parameters. It scales inversely with the square of the mass of the heaviest fermion, which is our dark proton. So that means that if we have a, you know, greater than GeV dark proton, we can have subsolar mass black holes. So how do we get from this very general picture towards you know, some more realistic forward modeling? So the first mass scale I mentioned is this opacity limit. The idea, when you know, the crude idea is at some point, if we have very optically thick gas, it'll radiate like a black sphere. And when this black sphere can no longer radiate its gravitational binding energy within a free fall time, then the collapse is going to decelerate and we're going to end up with like a hydrostatic object. So this basically gives you a mass that goes like the Chandrasekhar limit, the dark Chandrasekhar limit, with this additional weak temperature dependence. I want to remind you that this is like the mass scale where we expect to first form hydrostatic objects, but it's not the final mass of the objects. So for example, if this turned out to be much larger than the Chandrasekhar limit, then that would tell us, okay, we actually can't form black holes all the way down to the smallest mass that's in principle allowed in the theory. Now for atomic dark matter, that temperature dependence turns out to be quite non-trivial. And the reason is that in this case, the primary coolant at low temperatures is actually dark molecular hydrogen, and the molecular chemistry is out of equilibrium, which means that we actually have to solve a chemical network involving these dark molecular species. So this was a real pain. We wrote some papers about it. I won't go into too much detail here. but I think I'll just get to the point, which is that we did figure out how to do this. And so we can do the one zone kind of calculation that I mentioned, where to be a little bit more concrete, we're solving an ordinary differential equation for the temperature, where we have some compressional heating and some cooling, principally from the molecules. And then we're solving for, as well as the atomic and the neutral and ionized fraction, the molecular fraction and species like H2 plus and H minus, dark H2 plus and dark H minus, that is. Yeah, I think I have time to go into a little bit of detail here. So we have a package that does this for atomic dark matter. We have a chemical network solver called dark chrome. And we can do these one zone calculations where we're going to take a sort of baryon-like coupling strength for the dark matter. So we have these interesting dissipative physics. We're going to make the dark photon very cold, though, because in this regime, it's actually possible for the atomic dark matter to be all of the dark matter. And although it is true that even with this pretty cold dark photon, we still have some cutoff in the matter power spectrum. That means that we don't quite have very small halos. So we're gonna think about sort of a density and temperature characteristic of like a 10 to the 8th solar mass halo. And then finally, we're going to make our dark proton a bit heavier than the proton. And this both helps with these self-scattering constraints because we want to have, small centimeters squared per gram. So making the mass big helps. And then, we have this insight that the Chandrasekhar limit is going to go inversely with the dark proton mass. So this gives us this really distinctive subsolar signature, potentially. I will skip this, though, and get to the point, which is that we can do this one zone calculation. Remember, the density is not self-consistently evolved, so we have to make some assumption. But we can make two extreme assumptions, one where basically we keep the density constant, and the other where we have full pressure-free adiabatic collapse on the free fall time scale. And there is a lot of information in these figures, but the horizontal axis here is the ratio of the mass of the dark electron to the electron, and the vertical axis is the ratio of the dark proton to the proton mass. And then these white dashed lines I mentioned are related to this suppression in the halo mass function. So we really want to be to the right of these curves, so that we'll have a sort of CDM-like number of these halos. What we should read off is that, as we might have expected, it's possible for this minimum fragmentation mass to be, many orders of magnitude subsolar. So that's nice, but what we really want to know about is what's the final mass rather than the initial mass, and that's a harder question. And in order to start to address that question, I'm now going to turn back to baryons, because in this case we know the answer. So I want to build some tools and apply them in a case where we know the answer. And in this case, the answer, if we go back to this density-temperature relationship, is that gravitational instability sets in around this critical density where the cooling saturates, around 10 to the 3rd per cubic centimeter. And the mass of the collapsing cloud that would form, in this case, population-free stars, is characteristically around 1,000 solar mass, or about the gene's mass at this critical density. So I want to understand that better. And the details here may be a bit dense, but I think that what I'd like you to ultimately take away is that we can take this relationship between density and temperature, and without having to do anything like hydrodynamic simulations, we can build up a more realistic model for the collapse that now has some spatial information, like a 1D model. The way that we can do that is we can turn this relationship between density and temperature into a relationship between density and pressure, basically just multiply by n. So this is like a barotropic effective equation of state. And then we can use the insight that basically at every point along this collapse, as the density is increasing, we're going to have a gas core that extends of order the Jeans length. And so in detail, what we can do is we can say that, you know, deep in this inner region, we can solve this equation of hydrostatic equilibrium, where we're now using this equation of state, so we're like integrating along this curve as we go towards lower density. So in other words, this dp rho is supplied by this density temperature relationship. And in this way, we can construct this sequence of density profiles. And we expect that this quasi-hydrostatic solution will break down somewhere around the Jeans length, or at the Bonner-Ebert radius, to be more precise. So each of these colors truncates where this solution should break down at the Bonner-Ebert radius. But then this is actually more powerful than it initially seems, because these collapses are highly non-homologous in the sense that the inner timescale rapidly becomes very short compared to the outer timescale, right? So like the timescale here is very short compared to the timescale here. And that means that the density in this envelope hardly changes between the time when it's established and the time when we form a core at some very high density. So that means that because we know the density at some point is sort of order the Jeans density or the Bonner-Ebert density, it's going to stay around that value throughout the rest of the collapse. And so basically we can just connect these dots to get a density profile for the collapsing gas. And this actually agrees reasonably well with the predictions from simulations, as well as some analytic results and similarity solutions. And then we can take this sequence of density profiles as the collapse proceeds, and we can calculate the ratio of the mass enclosed to the Bonner-Ebert mass. So when this exceeds 1, the cloud is gravitationally unstable. And so here I have a sequence of central densities as we go from this color to this color. And we should read that, you know, always in the inner part we have like stable gas, but eventually this ratio exceeds 1 and gravitational instability sets in. And we see that in this case we do actually get back the right answer. So we have that gravitational instability sets in around this critical density, around 10 to the third per cubic centimeter. And further, we see that, you know, this ratio peaks, like we have the most gravitationally unstable gas right around 1,000 solar mass, which is also what simulations tell us is this characteristic cloud mass for molecular hydrogen cooling. So in some sense, this is a very narrow result, but I think it's a useful way of understanding gravitational collapse in a sort of general sense. If you want, then, you know, the mirror dark matter is one specific point in this atomic dark matter parameter space. And I want to emphasize just, you know, here's my takeaways, right? If we are so lucky as to get a subsolar mass merger, this is a dark matter detection. That's something that's very clear-cut. And, you know, in that case, what we need to do is this forward modeling problem, which is potentially quite thorny. But still, there are going to be some, you know, interesting takeaways, even if we can't know the dark initial mass function in full detail. Because the thermal physics of the gas imprints some characteristic scales on the collapse. And so I think it's likely that there are going to be some interesting statements we can make based on these kinds of arguments. Thanks.
Thanks, James. Thanks for